So hello, welcome to our lecture 3 of group theory. In previous lecture 1 I have discussed about what is a binary composition, the associative property, the commutative property, what is composition table, etc. And in lecture 2 we have done some problems on it. Now what we need to learn in lecture 3, first topic is what is a groupoid. First I take a set G and a binary composition not, and let AB belongs to elements of set G, and which and which implies A not B belongs to G, i.e. for all AB belongs to G implies A not B belongs to G. Then the algebraic structure like this, G naught is called a groupoid, which satisfies this property. Let me give some examples, like set of all integers with respect to a binary operation plus binary composition addition forms a groupoid, because if I took any arbitrary two elements, say minus 1, 2 belongs to Z, then the sum will also belongs to Z. The set of all integers and binary composition subtraction also makes a groupoid, because if I take any two integers and subtract them, they will belong to the set of integers. Similarly, like we can say set of all rational numbers under binary operation subtraction, under binary operation addition, set of all real numbers under binary operation addition, set of all real numbers under binary operation multiplication, or all real matrices of order 2 under operation addition forms a groupoid. Next, what we need to know is what is called a commutative group. Commutative groupoid. Sorry, it's a commutative groupoid first. So, if for all AB belongs to, the statement is like this: if for all AB belongs to G, where G naught is a groupoid, this is the given groupoid, and for all AB belongs to G implies A naught B is equals to B naught A belongs to G. Then this groupoid will be called a commutative groupoid. For an example, I can say Z plus is a set of all integers under addition is a commutative groupoid, because if we take any arbitrary two elements, 2, 3 belongs to Z, the addition 2 plus 3 will give 5, which belongs to Z, and 2.3 is equals to, similarly 3.2 is equals to 3 plus 2 is equals to 5 belongs to Z, and we can clearly see these two are equal to not 3 equals to 3 not 2. So this satisfies the commutative property. So a groupoid which is basically satisfying the commutative property is called a commutative groupoid. Some more examples of commutative groupoids are Z or set of all rational numbers under the binary operation addition, or set of all real numbers under the binary operation addition, etc. But here is a thing to notice, that even if Z plus set of all integers under addition forms a groupoid, but set of all integers under the binary operation subtraction doesn't forms a groupoid. So this forms a groupoid because if I take two elements 2, 3 from a doesn't form a groupoid, because if I take two elements 2, 3 from the set of all integers in this, and Just use the binary operation. 2.3 implies 2 minus 3 is equals to minus 1, where 3 not 2 implies 3 minus 2 is equals to 1. So clearly 2 not 3 is not equals to 3 not 2. So set of all integers under under binary separation subtraction doesn't form a commutative group. Why here I have to write, basically I was saying set of all integers under addition forms a commutative group, but set of all integers under subtraction doesn't form a commutative group. Next, in group 3, the next topic next topic which we will discuss is identity element. So what is an identity element? The definition says that let for all A belongs to G, if there exists an element if there exists an element E such that A naught E is equals to E naught A is equals to A, then this element E is called the identity element of the group. Obviously this E will belongs to G. Let me give an example so it will be more clear. For set of all integers under addition, under binary addition, 0 is the identity element, because if we take any arbitrary element A belongs to Z and add with 0 from left hand side or right hand side, it will return back that integer. So clearly 0 is the identity element of Z plus under addition. If I take the operation as multiplication, then the identity element will be 1, because if we multiply any integer with an 1, it will return that integer. So it's the identity will become 1. Similarly, then the next thing what we need to know is the left hand identity and right hand identity. What is left hand identity and right identity? The definition says that if for all A belongs to G, there exists an element E belongs to G such that A naught E is equals to E, but naught is the binary composition, obviously. A naught E is equals to A, where naught is the binary composition. Then this E will be called the this E will be called the right identity. As you can see, this is composing on the right side, so from that we call this the right identity. Similarly, if for all A belongs to G, there exists an element E belongs to G such that E naught A is equals to A. For all A belongs to G, then this E is called the left identity, as is composing from the left side. Obviously, this not is the defined binary operation on the groupoid. For becoming a, what we now need to notice, for becoming a left identity or a right identity, that element E belongs to G, just showing a partial of that property. Like for right identity, it have to satisfy the property E not A is equals to A, and for left one, this it have to show E not A is equals to A. For all A belongs to G, and for all A belongs to G. Let me give some examples of left-hand identity and right-hand identity. In the set of all integers under addition, 0 is the left-hand identity as well as right identity. Because if we add any number, add 0 from the right side of an integer or left side of an integer, it will return the same integer, so it's both left and right. But similarly for z not z under multiplication operation, the groupoid, in this groupoid, one is both left and right identity. But in z minus the z under my operation minus or subtraction, there is no left identity, as there doesn't exist E belongs to G such that for all A belongs to G, E not A is equals to A. So Z, E doesn't have an element which will become its left identity, but 0 is its right identity. So we can check these things by any examples, like if we subtract 0 from any positive integer, it will not return that positive integer, or if we subtract 0 from any negative integer, it will not return that negative integer, it will return a positive integer. So 0 can't become the left identity, but 0 in case of composing from 0 from the right side, this will clearly return the same integer for whether A is positive or negative or 0 itself. So 0 clearly becomes the right identity. So the next topic is, there is a proof. We have to make a proof. The proof statement says, if a groupoid G0 contains an identity element, then that element is unique. So let's do the proof. Our first proof of this series. For this proof, we will take we'll assume that the identity element is not unique. So we'll take E and F, two identity elements, of the group G. Then if E and F are two identity elements, then they will showcase these properties, like for all A belongs to G, E not E is equals to E not A is equals to A, and for all EA belongs to G, A naught F is equals to F naught A is equals to A, and clearly we since E and F are identity elements of this groupoid, E and F obviously belongs, by our assumption, will belong to the G, the set G. So we can again say E naught F is equals to F by property of E, and E naught F is equals to E by property of F. We just replacing the A here and E here, so using the simplest property and getting this things. Now by comparing equation, if we say this is equation 1 and this is equation 2, so by simply comparing we can say what? E is equals to F. So the what happened? E becomes equals to F. We assume that those identity elements are not equal and they are different, but we are finding that they are equal. So what we can say at the end, that our assumption is wrong and the identity element is unique. Next, what we need to know, there is another proof. The statement says that you have to prove if a groupoid contains a left identity as well as a right identity, then they are equal, and the equal elements is the identity element in the group. It's a groupoid. Later we will know what is a group. That will also show the same property, whatever. But so doing this proof, we are taking first assuming E be the left identity, let's see, I have written wrong spelling anywhere. No, E be the left identity, F be the right identity. Now from the property of E we can say for all A belongs to G, E naught A is equals to A, and from property of F what we can say for all A belongs to G, A naught F is equals to A. And again by property of E we can say, by property of E naught F is equals to what? F, obviously, because E is the left identity. Again by property of F now we can say E naught F is equals to what? E, because F is the right identity. So this is, let's take this equation 1 and take this equation 2. From equation 1 and 2 it's clear that E is equals to F. So the right identity of the groupoid is equals to the left identity. And now by previous theorem, that what previous theorem states what? If a groupoid contains an identity element then it's unique. We can say what? This is the identity element of the group. This E equals to F will become the identity element of the groupoid. So thank you. This lecture will end here. From the next class we will learn what is left invertible, what is right invertible, what is a right inverse of an element, what is a left inverse of an element, etc. So bye.